All right, since we are a minute out, I just want to welcome everyone. Thank you for joining us today. My name's Heather, and I have Justin Stover here from CC Jensen with me as well. He's going to be presenting most of the content today. Just a little housekeeping. If you run into any audio issues or have any questions in general about the content even, please feel free to put that in the question section or the chat section of the GoToWebinar menu. Otherwise, we'll be answering questions towards the end and we're leaving about 15 minutes for that. But if we have a lot of questions, we'll just end up keep going because we know that's pretty interesting for people. And if there's anything that we don't get to, we'll be sure to get an email back to you to answer those questions towards the end. So Justin and I are going to kind of be playing off of each other here, and we hope you find this interesting. Extending the lubricant life of your equipment is obviously the whole goal of why we all do this, right? We want to have uptime, maintain reliability so that we are not losing time and labor, resources. We want to optimize all of that. And one of the ways we do that is through lubricant or oil analysis. So when we're talking about that, there are really a couple goals and questions that we want to ask ourselves. So when we talk about this, there are really two questions to start with. So we want to talk about what is being monitored. Are we looking at the machine? Are we looking at the lubricants? Are we looking at both? Depending on what your goals are, each type of goal is going to require a little bit different test package to achieve that goal. If you want overall health, that is going to be a little bit different than specifically looking at the health of your machine. So we need to determine our test package to really help us start extending that oil life so we can look at the things we actually need to look at. And you can always, have an open dialogue with the lab that you use or any of your vendors. That's why we're here, is to help you out. And that's our goal as a business and what we like to do. So the second question you want to ask yourself too is, how often will samples be taken from machine? How often can they even be taken? When we talk about wind turbines, obviously you're only climbing those towers twice a year, if that at times. So you also want to look on the criticality and the type of testing, frequency of the samples in order to help you determine the best test slate for your machine. So today we're mostly going to be focusing on the oil analysis tests that are used, but something you want to keep in mind to have an overall view is the location of the sampling port, or where you're pulling the sample from, the criticality of the machine, like I said, frequency, target alarms development, and even selecting a lab. So we're not going to go into all of that today. I'm going to save that for another time, but we're going to be focusing mostly on the tests. And when you look at test slates, there are generally, I put this little kind of cheat sheet together. It's not a completely exhaustive list by any means, but this is something that Justin and I wanted to put together to share with everyone to give a good baseline. And the goal with this table is to give an overall view of what you may be seeing. So when we talk about certain types of equipment, like a gearbox, hydraulics, gas turbines, compressors, you're going to notice that there are some similarities between all of these, such as viscosity is one of the most important properties in a lubricant. So you're going to see we want to test that for everything. ICP is also a very useful, very popular tool to use because it gives you a really good assessment of your overall machine health, your lubricant health, and any contamination that's present. We also want to look for acid number, FTIR. I won't read through this whole list, but you'll notice where there's whole circles. Those are tests that you want to do on a routine basis. Where you see the semicircles, those are tests that you may want to do on an annual or less frequent basis. They're not necessarily things you need to do every single month or every quarter, depending on your sampling frequency. But there's a couple things that are interesting in here that I want to call out, because when you're looking at test slates, you do need to base it on the application that you're using, and as well as your environment. So if we look at the industrial gearbox, you'll notice that particle count does not have a circle indicating that it should be routine, but it does have a little asterisk in there. And one of the interesting points is that if you have an industrial gearbox that does not have any sort of filtration on it, there's not necessarily a point to running your particle count if you're not going to do anything to remove those particles from the system. However, we do see a lot of gearboxes that are utilizing filtration these days, whether it's a kidney loop or some sort of other functionality. And for those systems, we do recommend that everyone would use particle count testing. So something else that's kind of interesting that's application specific is when you look at the steam turbine column, we talk about running demulsibility routinely for that, but not for gas turbine, wind turbine, or many of the other applications listed here. And the interesting point with that is that with demulsibility is so important because it's looking at the ability for the lubricant to separate from water. And with steam turbines, you have the potential risk of a lot of water entering the system in quick succession. You don't really have that risk with something like a gas or combustion turbine or many compressors. And for that reason, it is so incredibly important that the lubricant has that ability and maintains the ability to separate from water in the steam turbines. So you're going to see, you'll have access to this chart in the recording, but if you do want it separately, feel free to let us know. I can get it sent out. But this is just a quick overview of routine test packages to use for some different applications. Like I said, it's not exhaustive, but there is a lot here. And it's so important to have this information so that you can accomplish the goals you're looking for and run testing that is appropriate for your application. So what is important too is to have an idea of what the various tests do. What is ferrous density looking at? What is foam looking at? What is ruler, MPC, viscosity actually looking at? And what can these tests accomplish? So Justin and I are not going to go into the technicalities of every single test method at this point. That will be saved for another time, but we want to go over and figure out how can we categorize these, because I know we can categorize these tests when we talk about machine health, lubricant health. So what information are we able to yield by categorizing these tests? And this is something that Justin is actually going to be helping us with. So I'm going to switch over to Justin as the presenter. And he'll be sharing his slides momentarily here with everyone. Oh, Justin, I think you're muted still. But let's see. There you go.
Okay. Well, thank you, Heather, and thank you all. First of all, just want to say thank you for joining today. It's a pleasure to be here on the webinar with you. And that question, how can I extend lubricant life? That's a frequently asked question that we get. We hear it. It's probably the #1 question that we hear. And it's a simple question on the surface, but the answer to that can be complex. And like with anything complex or difficult, you can answer that or tackle that by breaking it down. And by breaking this down into categories, it really helps us to be able to start to answer that question of how I can extend my lubricant life. And this reminds me of a story that I wanted to share with you, and I'll show my screen now. And let's see, I make sure we have. And can you see my full screen there, Heather, the slide? Okay, good.
We are looking at the presentation mode, not the full screen, though.
Okay, we'll swap it over. How's that?
There you go, that's it.
Okay, good. So I heard this story about a professor, Harold Pollack from the University of Chicago, and he was on a online video chat and was talking about the best personal advice that you can get. And he made a comment that, well, this can all really be fit onto a 3x5 index card. And afterward, after this online chat, he was flooded with questions from people asking, where can I get this index card? I'm interested in that. And so what he did is he took one of his daughter's 3x5 cards and just thought about it and jotted down some of these principles of financial advice. He took a picture of it with his iPhone, then he posted it online, and what happened is it went viral. People loved it because it's simple, it's good advice. And that's a similar concept that we can apply to many areas, including even this question of how can I extend my lubricant life? And so if we do that, if we just take some time to think about this question a little more, how can I make my oil go further and last longer? Well, it really starts with our attitude. How do we view it? Do we view it as an asset, not a waste product? And that's why we're here, right? Because we're interested in this topic and why many of you signed up for this webinar. And then we realize that we need to migrate from just simply time-based changes to condition-based changes. So we recognize that oil should be changed not just based on time, but on the oil quality properties. And then finally, treat the oil well. And then we can have a scenario where it's as many of our customers are striving for fill for life. It's interesting that the synthetic base oil has a 20-year life in most cases. So it's really not the base oil, but it's the additives, for instance, that are aging, or other properties, things that we can control that contribute to premature aging. And so with that in mind, then we can start to fill out our own index card, and we can do things very simply. Keep it cool, keep it clean, keep it dry. We recognize that if we keep it cool, this decreases the speed of chemical reactions. If we keep it clean, for instance, removing particles, even focusing on small particles, because these act as metal catalysts. And the smaller the particle, the larger the total surface area, and this can create a more catalytic environment and also deplete the additives rapidly. And if we keep it dry, we recognize that by lowering the water content, it reduces aging. And for instance, a lot of research about bearing life, that even dropping the water content from 300 ppm to 200 ppm can double the life of the bearing. And then finally, routine oil analysis, of course, because we want to monitor the health of the oil. And this all makes sense, doesn't it? Because why does oil go bad in the first place? Well, it's because the oil is contaminated, it's dirty, there's water, and we have to change it out. If it's stressed, it produces, or it results in oxidation, water, particles. This all contributes to chemical degradation. The oil breaks down. We see sludge and varnish, acid in the oil, the viscosity increases. And then finally, the additives deplete. And so that's, again, why it's so important to follow these basic principles so that we can monitor the overall health of the oil, the additive health, and that will help us to reach our goal of longer life. And so then now we can start to break it down into categories. And there's 4 that we want to focus on here. The first one is degradation. We recognize that when it degrades, the oil changes composition and its functional properties, and this results in unwanted properties that are formed: oxidation, acid, things like sludge and resin, varnish, and even the viscosity will begin to increase. And so lab tests that we can focus on for this are the viscosity, the acid number, and a host of varnish tests. The MPC, the RPVOT, and the ultracentrifuge will help with that. Another category is contamination. Particles and water are the 2 that we typically will focus on, and there's various lab tests that we can use to pinpoint that or identify those. The particle count, Carl Fisher water test, demulsibility, also air release, and foam. And then when we want to look at additives, this is a 3rd category. There's lab tests that we can use for that as well. The ruler, ICP analysis, foam, demulsibility, RPVOT, and the base number. And we see that there's some interchangeability with some of these tests between other categories, but they all help to provide a complete picture of what's happening with our oil. And then finally, the 4th category is qualitative analysis. Tests such as analytical ferrography, or as we see here, an example of filter debris analysis. We can send in our used in-service filters and have those analyzed, and it provides much valuable information. So again, by summarizing all of this, we can keep the oil cool, keep it clean, keep it dry, and then continuously monitor it through routine oil analysis and even additional oil analysis tests that can help us to identify any potential problems and then how we can extend the life of that lubricant. And this really underscores the importance too of what Heather discussed earlier of good dialogue, ideally between the equipment manufacturer, the oil company, of course, your lab, and your contamination control supplier.
So I know when we were talking about setting up this webinar initially, we were doing a lot of discussing about contamination, and I've had a lot of experience with reliability professionals and plants in various places that have just tested particle count, and that is it. That is the only thing they're using. And sometimes I worry that there's a little bit too much focus on ISO codes, and I think that's a little bit more of an older school thought. Obviously, it's very useful in filtered equipment, but sometimes I think we're trying to extrapolate too much information on the overall health of the system. And I know this is something that you have some thoughts on too, if you want to share those.
Definitely, and we do see that or get that response quite often, and we recognize that if you're just focusing on the ISO codes, that's good. That's the front line of defense, but we want to go beyond that. And this next slide helps to illustrate that. As we look at the oil, of course, particles and water are important to focus on, but there's other things that we can look at that really help us to get the whole story of what's happening with the oil. Now, if we look at the upper left there, the oil drop, the particles may be what we consider normal. It may actually be a clean ISO code by some standards. But as you look at this oil, in this case, is this going to last its full life? If you have water, as we discussed, if there's oxidation occurring, now you have a catalytic environment where the additives are slowly being depleted, and that can increase rapidly. As you mentioned, the wind turbine, if you're just taking a sample once a year or twice a year, in between those samples, this can increase. And then the result, of course, is that you have these oxidation byproducts, resin, sludge, and varnish. And so when we use other tests that we've discussed, then it gives us a complete picture that maybe the ISO code alone isn't telling us, and it can help us to identify the early onset of degradation of other problems that can really help us address those and then get that longer life that we're striving for.
Yeah, I completely agree. And you know, one of the points that I like to make when we're relying just on ISO codes is that when you look at particle count, there are a couple different types of particle counting technology, and some of those look at only hard particles like metals and dirt. Some of them only look at soft contaminants like sludge, oxidation byproducts, water droplets, air droplets. So particle count is definitely a good start. It helps you start to see a trend, whether it's up or down, right? And I think the other tests really help come into play because while particle count gives you a trend, they really are the supporting evidence for what else might be going on. And, you know, I know that when particle counts decrease, that can indicate that additives are being stripped, or at least I've heard that assumption at times, or that maybe you're filtering too fine. And I know this is something that we talk about a lot. I get this question constantly. And do you think that real fine filtration can actually remove these additives that are essential to the oil to extend the life, and what we're trying to accomplish by monitoring these with these other tests?
That's another great question, and we'd probably rank that number 2 in the most frequently asked questions that we hear, right behind extending oil life. And it's an important topic for sure. We recognize that because additive depletion tells us a lot. It tells us about the remaining useful life of the lubricant. And there are various methods available through a lab to look at that. We can track the additives for a reason. We want to know, first of all, if it's there. And then secondly, we want to know how much of that is remaining. But there's also another truth about additives that we need to recognize, is that they are, when they're properly blended, they should be fully dissolved in the oil. So we always liken it to sugar in coffee or in a soda. And you know how hard it is if you try to remove that sugar from those drinks. It's extremely difficult. And as a filter company, we like to think that we're pretty good, but we're not that good. It's on the order of magnitude that we can't even begin to touch those dissolved additives. So when we think about it too, additives are sacrificial by design. That's actually what we pay for. We want them to deplete. We want them to do their job and to sacrifice themselves for the health of our equipment. And so there's, of course, other mechanisms at play here that we need to recognize. One is decomposition from water and heat. That can cause the chemistry to change. The mass of the additives is still floating around, and it's possible that that can be detective. But there's also the situation where you have mass transfer of those additives.
Yes.
For instance, detergent and dispersant additives, they'll latch onto a particle to keep it finely divided and suspended, so it can be eventually filtered out, which you want it out in that case.
Oh, of course, yeah. If it's degraded, it's not doing the job, and oftentimes they act as a catalyst to cause even more degradation.
Exactly. And what I want to do is show a slide here talking about anti-wear additives. By design, these will actually put down a layer on frictional surfaces. And I'll just share here some information about that, a lot of information here. But again, these are additives that are dissolved, and they will become deactivated at some point by laying down this additive layer on the metal surface. And so therefore, we can conclude from this that that once those anti-wear EP additives, as it mentions there, have been deactivated, then they can be removed by fine filters, which is a scenario that you want, because at that point they're spent additives. You no longer want them in your oil. Another area we can look at is antioxidant additives. Oil, as it oxidizes, we've touched on this, it produces these organic byproducts. It leads to the formation of varnish and sludge. And this will create an environment where you're actually depleting the additives even further, because you're not controlling that varnish and sludge. And what occurs is we see here is it increases the acid number, it increases the viscosity, but we recognize that by filtering at a fine level, you will not remove these dissolved antioxidants. What you will do is you'll remove particles, you'll remove the moisture. It also helps to control the heat, and it will delay the onset of further acid formation and varnish formation. And so we can conclude again that fine filters, they will remove the oxidation byproducts, they'll remove particles, they'll remove these catalytic type particles, and overall it helps to avoid the faster consumption of antioxidant additives, therefore extending the life of the oil.
No, I completely agree. And that's a question we get pretty routinely too. You know, and that's why we run tests such as Ruler or RPVOT to try to make sure that we're monitoring those as well. And you'll see those on the initial test package recommendation chart for that reason. But I think, so we definitely know that monitoring lubricants using specific tests will help us understand how we're doing with the lubricant. But something that always comes into play with extending the lubricant life is we know we are going to run into problems at times. It does happen. So once we counter a problem, such as high acid number or water ingression, can we still work towards extending the life of that lubricant?
We certainly can, and that requires, in our world, the use of specialized kidney loop filtration equipment that's been designed to address those specific contaminants. If we identify, for instance, that we have a high level of varnish in our varnish test, our MPC and UC reveal that, then we want to address that. And there's equipment that we can use to remove those contaminants from the oil. Same with water. Water can be tricky, but there's different forms of water. There's free water, there's dissolved water, there's emulsified water, and there's different techniques such as air stripping or a coalesce, or even just simply absorbing the water if it's at a lower level that can help to address that issue.
Mm-hmm. No, that's absolutely right. And that's usually the recommendation that I give people as well. But when it does come to using these technologies to help you mitigate some of these issues, especially with water removal, you also do have to take into account the type of lubricant that you're using, because that you may or may not have solubility issues with any filter media that you might be using with it as well. So that's something to definitely keep in mind. And I know you and I have talked that something people always want to see too are case studies, because it helps bring this to light a little more, it helps it application. I know you and I are big on application. Theory is nice and helpful when you're learning, but a lot of people just want to know, what does this actually look like? And I know you've prepared a couple for us today, if you could for those.
Yeah, I'd love to. And going back to what we discussed before about the index card, so we have that those basic principles. We want to keep it cool, clean, and dry. We're using analysis, and then we identify a problem, like in this case with a wind turbine and the hydraulic pitch system. They identified that they had a relatively high particle count. It wasn't off the charts, a 16, 15, 8. They were using a microscopic method, so they're looking at particles larger than 2, 5, and 15 micron. A little different methodology, but still the same result. They saw that it was a little higher than they wanted, but what really jumped out was the water content, 1,800, just over 1,800 parts per million. So that's what the oil analysis helped to show them, is that they needed to address this and keep it dry, and not only keep it clean. So the decision was made to upgrade that system with a fine filter, an offline or kidney loop filter as it's often referred to. And we can see the results here. And here's another example of, if you're just focusing on ISO codes, one could conclude at 16, 15, 8, well, that's pretty good.
Mm-hmm.
If you're just looking at that, but you miss the water. And what visually they were able to see was how oxidized the oil was. And so that was a potential here too, that they could have employed some further varnish testing to look at that and see where that was. But the good thing was they took a step to mitigate the problem, and you can see the excellent results, being able to reduce the water levels below 100 ppm and bring the ISO code down to even the single digits on the larger particles. 11, 10, 7 was the final result. So that's one case study. And another is also a wind turbine, but this time looking at the gearbox, the gear oil. And this was a newly commissioned turbine. And in the summertime, the first sample came back extremely high particle count, 2018, 15. There was high iron and too high of water content for a new turbine, a new gear oil of 390 parts per million. So that's where routine analysis helped to identify the problem, and again, taking those steps to keep it clean, keep it dry. At the end of June, it was upgraded with an offline filter, a fine filter. And you can see from June 30th to May 10th, there was significant progress. But then the decision was made, because of this middle sample and the analysis showing that there was still water, still some iron, they wanted to bring that down even further. So the filter insert was changed, and the very next day, the oil was sampled again. Wow. And you can see visually just what an improvement, getting down to 16, 11, the iron dropping to 1 ppm, and the water down to 40 parts per million. And what was interesting with this too was exploring this even further, was looking at the qualitative category that we discussed, filter debris analysis. And from this turbine, it's interesting to see that the iron, as we can see, was quite high. And this is actually what the filter had captured through using the filter debris analysis that test oil provides. And you can see the two different patches that are used, the 30 micron and the 5 micron. And the largest percentage of those patches is iron and then also calcium. So it led to the question, well, what was occurring? Well, it's quite easy to conclude here that it was iron that was one of the major contaminants, and the calcium was one of those detergent dispersant additives that was latching onto these iron particles, which in turn they were filtered out. And so having this type of analysis available to qualify it, to really help to get the whole picture of what's happening, and also proving the performance of the filter, that it really was doing a good job for this gearbox. And subsequently, this oil has remained in service for many years since this initial cleaning up. The owner was looking at replacing all of the oil, replacing the gearbox even, but instead, just by using routine oil analysis and good filtration, they were able to keep that oil in service, which really is a huge benefit, because for the average wind turbine, the cost savings of if you just look at one oil exchange, it's a conservative estimate is $5,000.
Yes.
If you look at a wind farm of 100 turbines, that's $500,000 or $500,000 over the life. And that's even more critical when you look at offshore turbines, which the cost there can be 2 to 4 times that cost.
Oh yeah, I have heard some of the costs associated. That's something that I will often ask when I talk to a customer that has experienced something. And that's interesting about filter debris analysis, because just a quick story, something that I've run into a number of times is someone probably like similar to your person, they'll know that there's something wrong. There is some sort of issue. And they'll send in an oil sample, everything looks good, it comes back normal. They don't see there's no evidence in the data for me to tell my customer that I can definitively tell something's wrong. But I will often ask that they send in a filter for filter debris analysis, because I assume if people like Justin and DC Jensen are doing their jobs, their filters should be working and collecting that debris so that it's not in the lubricating system moving through the critical components. And that is often the case when the oil analysis is normal, we will find something in the filter because the filter is doing a good job of collecting that debris, meaning that they made a valid investment there. So that's something I completely agree with. But otherwise, I do see we have a couple questions here. There were a few questions I was answering throughout the webinar, but there were 2 that I wanted to save because they seemed like good points of discussion for us. The first one is that there are companies that will replace additives once they are depleted. Is this recommended, and what are the risks of using this approach? So a couple thoughts I have on that is that I think it's dependent upon the application and the system. And anytime you go to re-additize the system, you have to be extremely careful. I know I've seen a number of horror stories where people have used basically splash. They just throw it in the tank and they kind of let it do its own thing. And this legitimately happens to this day. And then it just becomes this kind of gooey mess because the additives are all conglomerated into one another and it forms a sticky gel basically that then coats critical components of the system. So that it can be done. I think you just have to be very careful about it. You want to use a reliable company to do that, and you want to take into account the application that you're using. There are some applications where this is pretty routine. I know I've been hearing about this more and more with some turbine oils, and honestly, I've been seeing some success with it. So it can be recommended. That would be something I highly recommend you work with your vendors on to develop number 1, a good procedure for doing this. Number 2, it might not hurt to do a mix of whatever the ratio is that you're planning. run some testing on that to make sure that the performance characteristics and the chemical composition characteristics of the lubricant are where you are wanting them to be at with that ratio. But I think it can be a good idea overall. There are a few cases, very few cases where I would not recommend it, as long as you're very careful. And next question, are there any filters available using transition metals to help decrease oxidation due to air entrainment? So for this one I am not as familiar with. The first one I can think of is phosphate ester systems. They will use some metallic type elements like calcium and aluminum, and their filtration is often known as Fuller's Earth or Selexorb or activated alumina. But that's more so to help with removing any sort of acidic components, potentially water. As far as decreasing oxidation due to air entrainment, it's those types of filtration are geared at removing oxidation byproducts. So not necessarily due to air entrainment, but you will see similar chemistries from air entrainment as you will to water entrainment. It'll just be a different form of carboxylic acid. And these types of filters are meant to remove those byproducts. I think that answered the question. Justin, do you have any other thoughts on that one?
No, that answered it well. And there are techniques out there, of course. I think it really, again, underscores the value of having good dialogue with your oil supplier, with your equipment manufacturer, and with your filtration or contamination control supplier, your vendor, to identify what really is the problem and then what specific techniques can be employed to address that.
Yeah, spot on. Let's see. We just had another one come through. Is there any possibility of the formation of water by chemical procedure in gear system? Is there any possibility of the formation of water by chemical procedure in gear systems? The formation of water. That isn't something that I would see too often in gear systems. There are some other types of systems, again, phosphate esters, phosphate ester lubricants, which are commonly used in EHC or electrohydraulic systems. They can produce water in the system. Most of the time, gear systems are using a polyalpha olefin oil, a PAO, or a mineral oil. Those don't typically form water through any sort of normal chemical reaction in most gear systems.
We do see that there are, on average, we would say the water content is very low in, for instance, wind turbine gear oils. And looking at, we have over 100,000 installations. Typically, the water content is below 100 ppm, anywhere from 100 to 200. There are cases, though, certain oils that are more hygroscopic that will show through Carl Fisher analysis that you can have 500 to 1,000 parts per million, but no free water. So that's more related to the oil formulation. But I would say water typically comes when there is a high water content at some sort of external source of water getting into the oil. A lot of times it's poor storage.
Yes. Yeah, poor storage, condensation due to extreme temperatures. If there is a cooling system nearby, even if you have systems that are stacked, we have seen issues where there's the cooling system may not even be connected or related to that gear system, but because of the how it's positioned within the plant, there could be a leak up here that then goes down to the gear system. Let's see. Okay, next question. What is the most common form of oil degradation leading to the need to flush gearbox oil? Is it metal, viscosity, etc.? So most common form of oil degradation leading to the need to flush gearbox oil. So we're talking about metal viscosity. My first thought, and from experience of what I see, it's degradation of the lubricant. Most of the time, the characteristics you'll see first is an increase in acid number, an increase in viscosity. You might start to see more metallic, where mostly iron in the ICP, because it's mostly going to be dissolved or the corroded iron, so you might start to see iron oxides that would be present on the ICP. That's the most common reason. So, and oxidation, that can occur for a number of reasons. It could be due to water present. It could be due to excessive heat. If you have a heating element in the system, you'll want to check for hot spots once in a while. And Justin, do you have any other thoughts? That's kind of the most common thing that I see, or people accidentally top off or mix the wrong lubricant in. That's the other biggest reason that I would see someone would have to do oil change.
You mentioned hot spots. Certainly that was my initial thought, but also maybe not enough oil in the gearbox.
That's a good point, starvation.
Yeah, and then particles, I mean, we talked about it in your matrix. A lot of times the gearbox is so dirty that a lot of times you won't even run a particle count in certain applications.
Yes.
But that can create, again, a very catalytic environment where you see the rapid depletion of additives because you have all these particles that are consuming that, and then further wear and tear, and that just starts, it's a snowball effect, and then that can lead to poor heat transfer, and then just increased viscosity, and then things just go downhill rapidly from there.
Yes, yes, they do. That's true. Looks like one more question is, what is resistivity a measure of? And I'm assuming Eric's asking that from the test package recommendation. So resistivity is a lubricant's resistance to conducting electricity. So most of the time we will see this again in phosphate ester fluids, a couple other systems, and really you're just looking to make sure that that lubricant does not conduct electricity. Insulating oils are a big one where you would have resistivity results in EHC systems, because most EHC systems you're using a phosphate ester because it is a fire resistant fluid. So one of the properties you want to look at is its resistance to conduct electricity so that it does not create a spark. And see, those are all the questions we have right now. Really good questions though. Let's see. Yep, I think we got all of them. So otherwise, that is all we have for you all today. If you do have any other questions, you can feel free to email us. My email is hvercillo, HVERCILLO @testoil.com, and Justin is justin@ccjensen.com. Otherwise, thank you very much for joining us, and I appreciate everyone's attendance today. Take care.
Yeah. If I could, Heather.
Thank you.
Thank you. Bye-bye.
Bye.